there is a particular term which gives relevance to this particular effect, and that particular term is work function. The electrons which are on the surface will absorb this energy, they will gain this energy, and they will just escape from the metal surface. When light or radiation of suitable frequency incidents a metal surface, an electron is subsequently emitted. Quantas means it is very small discrete units of energy which is being propagated through space and time. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to start a new chapter here today, and that is dual nature of radiation and matter. So what is this dual nature and what is so special about matter and radiation? So this entire chapter will be an explanation of a particular experiment you all know that is done by a very famous scientist, that is Sir Albert Einstein. So this chapter will be just an explanation of his famous photoelectric equation regarding what the photoelectric phenomenon is, how that equation came into place, and what exactly are the terms of that particular equation. So let's get right on to it. So what is photoelectric effect? The photoelectric effect states that light of suitable frequency, if that particular radiation incidents any metal surface, then consequently electrons are emitted from that metal surface without any time delay. This particular process is known as photoelectric effect. Now, this is not found out by Einstein. It was actually observed even before Einstein came up with his famous photoelectric equation. Einstein won and was celebrated for the famous discovery of the equation for the photoelectric effect. He mathematically proved, why photoelectric effect happened. He's not the person who carried out the experiment, and he's not the person who stuck around in the lab. He's the one who theoretically formed, why the photoelectric effect happens. What happens to the energy? Why this phenomenon is happening just like this? That is what Einstein did. So again, the definition of photoelectric effect is that when light of suitable frequency falls on a metal surface, electrons are emitted, and this particular phenomena is known as photoelectric effect. The main thing you have to note here is that light of suitable frequency, because not every particular frequency of light, not every wavelength can actually produce photoelectric effect. Depending on the metal surface which you are using, depending on the conditions of the metal surface, and depending on the frequency of the ray which you are using, photoelectric effect can happen and cannot happen. So we'll actually learn about what are the minute details of photoelectric effect, but first you need to know what photoelectric effect is. It was actually Leonard and his colleague who actually observed, the phenomenon of photoelectric effect is taking place. So why this is happening, they couldn't find out experimentally. So they sent their results to Einstein, who later derived a mathematical relation for photoelectric effect, for which he won the Nobel Prize in later 1920s. And that is what we are going to learn in this particular chapter. So again, photoelectric effect is the phenomena in which when light of suitable frequency incidents a metal surface, an electron is subsequently ejected. Now, there are certain conditions for that phenomenon to occur. And the first thing you have to know about this particular effect is that there is a particular term which gives relevance to this particular effect. And that particular term is work function. So who is doing this work and what is this work function? So work function is actually explained as the minimum energy that is required by the electron in order to escape from the metal surface. And this is actually known as the work function of the metal. That is, if this is a metal surface, when a light of suitable frequency incidents this particular metal surface, an electron has to be ejected. It has to be plucked out, right? So this particular frequency of light has to do a certain amount of work on this particular metal. It has to impart energy to that particular metal surface so that the electron can be ejected. So again, the minimum energy required by that particular radiation in order to pluck out that particular electron or help the electron escape from that particular surface is known as work function. That is, the minimum energy this particular ray should contain in order to help the electron escape from the metal surface is known as work function, which is indicated by the letter phi. So the phi will indicate what is the work function of that particular metal. And this particular phi, that is the work function of the metal, actually depends upon the nature of the material used. That is, it depends upon which metal you are using. For example, are you using iron? Are you using cesium? Are you using sodium? Are you using gold? Depending on the various type of materials you are using, the work function for that particular metal actually varies. It might be easier or it might be harder depending on the metal you are using. And one thing that also affects this is the surface conditions of the metal. If there are impurities present on the surface, it might be harder. Maybe it is easier. We cannot say until we are sure of what are the impurities present. So, the factors that affects work function are the surface conditions of the metal and the impurities on the surface, or simply the surface conditions of the metal. So again, what is photoelectric effect and what are the properties affecting it? The nature of the material used, that is properties of the metal, and the surface conditions actually affect the metal. But there is one more thing. When we are imparting this energy, how are you going to define that energy? We cannot say that, okay, 1 joules of energy was given, 10 joules of energy was given. We cannot define classical and quantum mechanical terms together. We need an actual new unit for this. So actually what physicists usually use is that for the subatomic particle or simply for nuclear physics, when we are dealing with energies in terms of very small particles, the term we use or the units we actually take is known as electron volts. So energy from this point onwards will be defined in terms of electron volts. That is, 1 electron volt will be equal to 1 EV will be equal to 1.6 into 10 to the power minus 19 joules. So, if you ever have your values in joules, you can easily convert it into electron volts. 1.67 into 10 raised to minus 19. So, 1.6 into 10 to the power minus 19 joules. So this is equal to 1 electron volts. Basically, if you have opposite potentials, that much energy is required in order to accelerate 1 electron from one end to the other end. That is defined as 1 electron volt. So again, for subatomic particles, it is usually this particular value or this particular unit that is taken in order to express its energy. So again, since energy is mentioned, since how much energy is required, how much is the value of work function, all this will be termed and defined in terms of electron volts from now on, because again we are not using joules. Joules is for standard classical measurements, and for subatomic particles we just use electron volts because it's much more easier, because it's a much more fitted unit to measure subatomic particles energy states. So the next one is electronic emission. So what is this electronic emission? We just saw that, okay, photoelectric effect is the effect when light falls on, light of suitable frequency falls on a metal surface and electron is ejected or emitted. So that particular phenomena when an electron is emitted is known as electronic emission. So is photoelectric effect the only way in order to produce this electronic emission? No, right? So electronic emission, so let's say that this is electronic emission. Electronic emission can actually take place in a variety of ways, such as thermionic emission. So what is this thermionic emission? Thermionic emission means that when the metal surface is heated enough, then we can say that the electrons, the surface electrons will have enough kinetic energy to break those bonds and escape from the metal surface. So as you heat a metal, it expands, right? That is because it is gaining energy. The molecules are vibrating. So just like that, when you're giving heat to a particular system, let's say the metal surface, then the electrons which are on the surface will absorb this energy. they will gain this energy and they will just escape from the metal surface. So that is possible through heating the metal surface, or simply it is known as thermionic emission. So that is one form of emission. The next form of emission is very simple, what we just learned, and that is photoelectric effect. Here in this particular case, it is photoelectric emission. So when light of suitable frequency falls on a metal surface, an electron is emitted, and that is known as photoelectric emission. And finally, there is one more thing you can actually use, and that is known as field emission. So what exactly is field emission? So field emission actually means that when you're subjecting a particular metal surface in order to very strong electromagnetic fields, or simply electric fields, you can just pull out the electron from the metal surface, or you can just push out the electron from the metal surface. That particular type of emission where you're using very strong electric fields in order to emit an electron from the metal surface is known as field emission. So again, for electronic emissions, you have three processes to study. One is thermionic emission, which just means that you heat up the metal surface so that the electrons get enough energy and they are ejected. And then there is photoelectric effect, where light of suitable frequency actually produces the electron that is emitted. And finally, there is field emission, where the metal surface is exposed to high electric fields so that the electron is emitted or just plucked out. So these are the three types of emissions which you should know in this particular chapter. So the famous photoelectric equation, we are going to enter the mind of Einstein and see what he actually envisioned. So what is the process? That is the first thing. We already learned that, okay, when light or radiation of suitable frequency incidents a metal surface, an electron is subsequently emitted. So why is this happening? Everybody knows that, okay, this is related to some form of energy. But how should we take light? Should we take it as a wave or a particle, or both at the same time? Nobody knows. So what Einstein actually did was, he borrowed several ideas that was already constructed by the pioneer of quantum mechanics, that is Max Planck. So again, what Planck imagined was that, okay, light or beam of light is not one continuous ray, rather it is very small packets of energy which are propagating as very small discrete unit of energy. That is, light ray that is observed like this. Let's say this is a ray of light. He said that this is not one individual ray of light, rather it is very small packets of energy, very small discrete units of energy which is propagating through space and time. And Einstein took this particular idea and said that, okay, this might be the case. Let me look at it from this particular angle. Let me see that if I can explain photoelectric effect using this particular idea of Max Planck. So the first assumption he took was, okay, radiation energy. Radiation energy just means the energy of the incidenting beam of light, or suitable radiation which is incidenting. So that particular radiation energy is actually discrete units of small energy, or small energy packets, is made of small discrete units called quantas. So understand that quantas means it is very small discrete units of energy which is being propagated through space and time. So every radiation, or every wave for that matters, will carry the small packets of energy which is known as quantas. Quanta means very small. So quantum particle just means that very small particle. Quantas means that very small discrete units of energy that is distributed through space and time. So Einstein assumed that, okay, this particular incident radiation is made up of very small packets of quantas. Each second, one small packet of quanta is incidenting. So with that, he assumed, okay, since energy is directly proportional to frequency mu, that is, as frequency increases, energy also increases. We learned that in the previous chapter, that is EM waves. We learned that, okay, as the frequency increases, the energy of a wave also increases. That is why gamma rays are very deadly. So E is directly proportional to mu. So again, in order to avoid this proportionality sign, the constant we are using is known as Planck's constant. So E is equal to h mu, where h is known as the Planck's constant. And this particular h mu is the small quanta or small packet of energy which is being distributed through space and time. So E is equal to h mu, the famous equation in which he won the Nobel Prize. So it is not E is equal to mc square, he won the Nobel Prize. He actually formulated that theory, and that is known as the general theory of relativity and the special theory of relativity. But the equation that won him the Nobel Prize is actually E is equal to h mu. That is, energy is equal to Planck's constant times the frequency of the incidenting radiation. Now, the equation is not complete yet. Now, why is this E is equal to h mu? Okay, we know that, okay, this particular ray of light now has an energy that is h mu. But what is this energy used for? This energy is in turn used to free the electron in the metal surface. Or simply you can say that this particular energy h mu is used to free the electron from the metal surface. So again, the minimum energy you need to free the electron is already known, and that is called as work function of the metal. So some of the energy is used in order to free the electron. That is, h mu is coming like this. Some energy is used in order to free up the electron from the bounds of the metal surface. Now the electron is free. Now the rest of the energy is used. In order to give the electron a push, or simply an energy in order to move, that is known as kinetic energy. Let's take maximum kinetic energy. So remaining part of all of the remaining energy is now being used as the kinetic energy. So we can say that the energy which is incidenting like this is used to free up the electron from the metal surface, and the remaining part is used to give the electron a push, or simply an energy in the form of motion, and that is known as kinetic energy, half mv square. Or again, you can rewrite it as h mu minus phi will be equal to Ke max. Or simply, the electron which is emitted will have a kinetic energy which is equal to h mu minus phi. That is, how much ever the incident ray had the energy, that is h mu, from that whatever energy was required to free the electron from the metal surface is subtracted, and that much energy will be equal to the kinetic energy of the electron that is now being emitted like this. The electron will have a kinetic energy which is equal to the difference of work function and the energy of the incident radiation. But again, this is not a proper equation. I don't feel like this has any beauty to it. So how can you define or make it a little more pretty? So again, we know that, okay, work function is the minimum energy that is required in order to free the electron from the metal surface. Right. So again, this particular work function means that it is the minimum energy required to free the electron from the metal surface, which means that how much ever the ray is having energy, a part of that energy is being used to free up the electron, and whatever energy is remaining, it is given to the electron for the kinetic energy, for the trip as fuel. So what if I reduce the frequency to such an extent that it has only enough energy in order to free the electron? That is, it has enough energy to do work function, that is to give the minimum energy that is required for the electron to be just free. I don't give any more energy so that the kinetic energy is a positive value. That means that I'm giving no extra energy for the electron's motion. I'm only giving sufficient energy so that there is only work function, enough energy for the work function, that is just to free the electron from the metal surface, which means that I'm giving kinetic energy as 0. That is, there is no kinetic energy and only work function is being done, which means that in this particular equation, I can say that, okay, h mu is actually equal to phi plus 0. That is, the incidenting wave will only have, or the incidenting radiation will only have enough energy to just free the electron from the metal surface, but not to propel it forward, which means that h mu will be equal to phi. So this let us call as phi naught and this as h mu naught. So phi naught will be equal to h mu naught. Why I'm calling it as phi naught and h mu naught, I'll tell you. But so phi will be equal to h mu at this particular point where kinetic energy is 0, right? So if I substitute this particular equation into this particular equation, I can say that h mu minus h mu naught will be equal to Ke max. Or simply one more way of representing it is that you can just take the h common factor outside and then you can just simply write it as, I'll write it here, you can just simply write it as h into mu minus mu naught is equal to Ke max. So h into mu minus mu naught is equal to Ke max. So again, why did I do this? What is so special about this equation and what is it? How much is it different from this particular equation? So the difference is that, okay, here there is a quantity known as mu naught. So what is this mu naught? So mu naught is actually, it is the minimum frequency required by the incidenting radiation in order to produce photoelectric effect. That is, below this particular value, there will be no photoelectric effect. At least you need this particular value or above. Then only you can produce photoelectric effect. So this particular value at which photoelectric effect can happen or above which only photoelectric effect can happen is known as the threshold frequency. So this is known as, the value mu naught is actually known as threshold frequency. So threshold frequency can be defined as the minimum frequency that is required by the incidenting radiation in order to produce photoelectric effect, and that is known as threshold frequency, which is indicated by mu naught. And this particular equation signifies that. So always remember, mu will always be greater than mu naught. Okay. Now the last effect is photocurrent. So what exactly is photocurrent? So let's do an experiment and find out what is photocurrent. So imagine that I have an experimental setup just like this. So again, there are two metal plates here. Let's say C and A are two metal plates where C is known as the collector plate and A is known as the emitter plate, or simply the cathode and anode. So again, C is the cathode which attracts cations, or simply the positive ions are attracted towards the cathode and the negative ions, for example, like the electrons, are attracted towards the anode. Anode means that it attracts anions, which means negative ions. So you can see that, okay, this is an emitter plate and this is a collector plate. So why is it known as emitter and collector plate? I'll just explain. So in your textbook, it is actually a complicated figure. It's always good to know that particular figure so that you can draw that particular figure and understand that particular figure. But the experimental procedure is basically the same. So imagine that I have these two metal plates and in your textbook, it is kept in a vacuum tube and there is a special place where the radiation can seep through. But here I'm just using a simple mechanism so that you can understand this figure. So again, there is two metal plates separated by a distance and one is positively charged and one is negatively charged. And you can see here that One is negatively charged and one is positively charged. Always remember, the positive side of the battery will be connected towards the anode so that it can attract negative ions. And the negative side will be connected to the cathode so that it can attract positive ions. So this is cathode and this is anode. Don't ever forget that. So again, imagine that these two metal surfaces are connected to a battery, which obviously means that there is a potential difference between these two plates. Now, I am going to do photoelectric effect here. That is, I am going to produce photoelectric effect in this particular condition. So, I allow light of suitable frequency in order to incident that particular metal surface. So, what will happen? When light of suitable frequency incidents a metal surface, photoelectric effect happens and an electron is emitted. So when this electron is emitted, obviously it is being emitted into a field. That is, there is a potential difference across these two plates, which means that the electron is now being accelerated towards the opposite end, or simply it is attracted by the anode. The negative particle is being attracted by the anode, which means that the electron will move from C to A. So what happens when a negative charge particle like an electron move in a circuit? It produces electric current completing that particular circuit. So here electric current is produced by electrons which are produced by photoelectric effect. So this particular process where photoelectric current or photoelectrons are actually used in order to produce electric current is known as photoelectric current or simply photocurrent. So again, we can just define this particular experiment as when radiation of suitable frequency falls on C, that is known as the cathode, or simply here in this particular case, that is the emitter plate because it emits electrons. So when it falls on C, electrons are emitted and this is collected by A. This is collected by A means it is collected or the electrons are attracted towards the anode. So it is collected by A, which is also known as the collector plates because it collects electrons. And since this electron is accelerating from C to A, which means that it is producing a current. When electrons move with respect to time, it produces a current, and this particular current in this particular situation is known as photocurrent. So what exactly photocurrent affects, how the properties vary, like what are the nature of photocurrent, how it can be affected, manipulated, everything will be discussed in the very next session. Up to this point, the only thing you need to know about photoelectric effect has been discussed. Further things will be discussed in the very next session. So I hope you have understood everything about photoelectric effect I have explained here today. In the very next session, we'll learn how certain properties are manipulated or certain figures are affecting photocurrent. So until then, thank you.